Hello everyone. In today's video, we are going to solve another problem live on LeetCode from top interview 150 problem list. So far, we have solved all the problems up to H index. If you haven't looked at my videos where I solve those problems, please go to my channel and check them out. So the next one is insert, delete, get random O of 1. Okay, so let's make this a bit bigger and see what this problem is about. So implement the randomized set class. Okay. Randomized set method, which basically means the constructor initializes the randomized set object. Bool insert into val inserts the item val into the set if not present. Returns true if the item was not present, false otherwise. Yeah, basically it returns true if it was able to insert, and if it was already there, it wasn't able to insert, so it will return false. That makes sense. Bool remove int val removes an item val from the set if present. Okay, returns true if the item was present, false otherwise. So this is opposite of insert, where if it was not there, it wasn't successful in removing, then it will return false. And it will return true only if it was there. Makes sense. And it will remove it, of course. And then the last operation is int get random returns a random element from the current set of elements. It's guaranteed that at least one element exists when this method is called. Each element must have the same probability of being removed or being returned. Sorry, it's not removed. In this case, it's just returned. Okay, makes sense. And then you must implement the functions of the class such that each function works in average O of 1 time complexity. Okay, that makes sense. Let's look at the input examples. Well, there is only one example, looks like. Okay, so the way they have given input is very interesting. Basically, these are the operations on the data structure. And yeah, looks like these are the corresponding values. So basically, initially we just randomized set is constructed, so no values needed. Insert needs a value, so insert 1, that returns true. Yeah, 1 wasn't there, so remove 2, that returns false because 2 isn't there. Insert 2 should return true. Get random doesn't need any things, it returns 2. Well, it could have returned 1 or 2. Yeah, it says that there, just this example shows 2. Remove 1 is true. So now, because 1 was there, it is removed. Now there is only 2 in there. Insert 2 should, yeah, false. 2 is already there. And now get random. Yeah, that will return true because there is only 2 there. Okay, so that makes sense. Let's look at the constraints. The values are between negative 2 to the power 31 and 1 less than 2 to the power 31 inclusive. Yeah, this is just the typical 32-bit signed integer range. At most 2 times 10 to the power 5 calls, so that's 200,000 calls, will be made to insert, remove, and get random. Okay, and there will be at least one element in the data structure when get random is called. Yeah, they mentioned that before. Okay, so that makes sense. Now, I mean, the approach for O of 1 time complexity, most of us know that for insert and remove, if we want both of them to be O of 1 time complexity, we pretty much have to use a hash map. And the reason is, just to summarize, is that if we use something like an array, for example, right, we need to store a bunch of things, so it has to be some collection. So let's say an array. Then insert could be of 1 because you could say, okay, I'm going to insert in the next available cell in the array, right? And that is easy to keep track of, like, oh, what is the next index where we should be inserting, and we can just insert right there. And that would be of 1. But then remove wouldn't be of 1, right? Because we would have to scan the array for the values to figure out which value needs to be removed. I mean, where is that index that that value lies, and we have to remove that. And then we have to push all the elements after that, like one cell before. And In fact, all the operations which require us to search for the location of a specific value in the array are not O of 1. Arrays are great at O of 1 for a random index or a lookup by index, but they are not efficient in looking up the value itself, right? And that in the worst case takes O of n time. So we could say, okay, what about like something like a binary search tree so that we keep all the values kind of in sorted order, and that would be better than an array in searching for a specific value, but it will still be O of log n to do that. In fact, the insert now also becomes O of log n, right? So anyway, so in summary, for making insert and remove O of 1 pretty much means we need a hash map, right? Okay, so now let's look at the third operation, get random. Get random. Okay, so yeah, this makes it very interesting, and I don't think we can directly do this on just a hash map. And the reason is because, yeah, hash map is internally implemented by an array for sure, but it is a sparse array, right? Like if you have an array of size, let's say 29, typically they are prime numbers, the size of the array. But anyway, there will be it could be filled like a location 3 and 7 and 19 and so on, but it's sparse array. But hash map does keep track of all the or the total count of elements inserted in a hash map, and it can return that by, I think, a dot size method or something. So we could generate a random number which is between 0 and size minus 1, but then hash map doesn't have a way of saying, oh, give me the element at this index, because the indices of the internal array of hash maps are meaningless. A lot of them could be empty and stuff like that. So hash map, yeah, it does have a dot values or something like that, or dot get values method, which can give you an iterator on all the values in the hash map. But again, I think, let me actually open this up. I think that is a collection. It is not it returns all the values as a collection, which you cannot really access by a specific index randomly, right? And that makes sense because, like I said, internally, yeah, there you go. Internally, oh, I didn't mean to click that. Internally, hash map keeps an array, but that doesn't, it's a sparse array. So it's meaningless for it to return values in a specific order, which can be accessed by random indices, right? Okay, so we can't do this operation with just a hash map. Now, actually, let's draw an example, because it looks like we have to combine a couple of data structures and keep them in sync. And get random would be best done with keeping everything in an array, right? But we do need hash map to make insert and remove often. So I think somehow we need to keep both of them in sync. Let's actually draw this. I have this whiteboard, virtual whiteboard app open. I think there is some, I've used a table. Yeah, this is the one I've used before. So let's make this reasonable size. Okay, let's remove some columns here. We just need 2 columns, so let's remove this. Basically, I want to draw a hash map, right? And let's say this is key. Oh, that's really small. Okay, and this is value, right? Let me just make all of their size the same. 1 sec. Okay. Hopefully that worked. Okay, let's test. Yeah, it did. Okay, let's align everything as well. I think it's just easier on the eyes. 1 second. Make this horizontally middle and vertically middle. Okay, so let's say that we have, let's add a few elements here, right? So let's say we have element 2. Let's say the second one is where the hash doesn't matter in this problem, at least 3, 2, 7, 3, 4, and 13. Let's say like that, right? Okay, so let's not worry about value for now. So yeah, so this would be very easy to quickly look up by the initial value itself, right? The value that we were asked to insert, because that becomes the key in the hash map. But what I'm thinking is, in order to make get random, let me copy paste this. In order to make get random O of 1, actually this we want to, let's draw the array as horizontal, even though both are kind of arrays. Let's draw array as horizontal and hash map as vertical. So let me remove a bunch of rows here. Remove row. Okay, okay, it doesn't let me remove multiple rows like that. So one sec. Sorry about that. I haven't used this too much, but I think this should work. Remove row and remove this row as well. Okay, so we just need 2 rows. And how many values we did? We insert 5. So let's just, here we need exactly 5 cells. And this is actually index. And then this is the value, right? Yeah. Okay. So let's, this is 0, 1, 2, 3, and 4. Okay. So what I'm thinking is, one sec. Okay, so what I'm thinking is that when we, let's say the order in which we insert is, to remind us, 2, 7, 3, 4, 30, right? So 2 will be inserted first. 7 is the next one, then 3, then 4, and then 30, right? So what we can do is we can use this to make get random of 1, right? And that's because, again, this is just store it in the next empty available cell, right? Available index, right? If we get one more, we will basically add one more here and store it. And we can use a data structure like array list, which automatically grows, so we don't have to worry. Okay. And when we are called get random, we can pretty much generate a random number between 0 and 4 inclusive and just look up the value there and return that. So the hash table doesn't really need to be used. And when we are inserting and removing, we use this, but we need to keep these guys in sync. So for example, let's say that we are doing insert operation, right? So let's say we insert first 2. First, let's say everything is empty. So when we are inserting the first 2, sure, we'll put it here at 0 and 2. But here, what we'll do is at 2, the value will be the index in the array. So that's 0, right? So here, this is the array index. And then similarly, let's say next we insert 7. So at 7, the value will be in the hash table for 7 will be 1, because what now happens is that now we say, okay, hey, when we want to look up by value very fast, then we take the hash table that will give us the location of that in the array as well. So if we need to remove it, we can actually remove this, right? Okay, so now that is our insert operation. So again, summarizing the insert operation, we find the next available index in the array list and we insert it there, and then we reverse index that in our map, right? Reverse index that, meaning that the value in the array becomes the key and the index of the array becomes the value, right? So 7 goes here and 1 goes there. Okay, so it's a reverse lookup allows us to do that, and that should be O of 1 operation to do both of those operations, because both of those operations are O of 1. Now let's figure out how to remove this. So let's say we are removing, let's say this array is now filled up. I mean, this data structure is filled up with 5 elements. And let's say we are removing, I don't know, like 7. 7 is somewhere in the middle. So let's remove 7, right? We are removing 7. We first want to find 7 quickly. So we'll go here and we'll find that 7 is in index 1 of the array. So, okay, great. Now we don't want to be removing this and make all of the elements after that pushed 1 to the left, because that's an order of n operation. But what we can do is we can just copy this 13 over here and updates 13 index in the map. So here, actually, I just realized I haven't filled up the whole map. So let's do that. Actually, 3 is 3, this is 2, and 4 is at 3. Okay, there you go. Okay, so we basically update the value of 13 in this one, and then we just erase the last element, and all of those operations are O of 1, right? So again, summarizing the remove operation, remove, let's say we are removing 7. The first thing we do is we go to the array and we go to the map and we find out where 7 lives in the array, right? Okay, 7 lives in 1. So now we take the last element of the array 13 and copy that into index 1, because remember we want to make the array smaller by 1, but we don't want to shift everything, so we are taking the last and copying in the middle, and then we remove the last element from the array and we update 13's index in here, and we remove 7 from the map, right? All of those operations are off 1 if you think about it. Okay, so that gives us O of 1 remove, and like we started, get random is O of 1. We started there, right? Because we just generate a random number between 0 and 4 inclusive, look up that number and return that. Okay, cool. So I think this approach will work. We'll have to be kind of very careful in going step by step in updating our data structures and keeping them synchronous to each other. Okay, so let's do this here. So now, as you guys probably already know, when you use collections in Java, you have to use objects rather than basic data types like ints or doubles and stuff like that. So the two things we need here are an array list of integer, capital I integer, which are integer objects, right? And one sec. There you go. And let's just call this the list, right? This is our list and the other one is the map. And I generally prefix my members with small m. You can use any convention that you generally follow. And then the map, or hash map rather, sorry, hash map. And the hash based implementation is important for O of 1, right? So hash map, and this is our m map, right? Okay. So those are the two things that are the private data that we need, and in here we just initialize them, right? So we say m list equals new array list, and I think this should work. We don't have to give the data type here. I think it implicitly figures it out. And m map equals new hash map, and then we do the same thing here. Okay, there you go. So we are initialized. Now let's do the insert. Now actually in insert, remember there is one more detail, right? If the element already exists, we need to return false. So let's do that first, right? And again, checking that it exists should also be order of 1, because the whole operation needs to be order of 1. And hence, where do we check when we are trying to look up by value? We check the map, right? So if map dot contains key, I think, well, then return false, right? I'll just quickly check that that's the method. Have map thing open here. Yeah, contains key, there you go. Okay, so that's return false. And now we do our insert algorithm, right? How do we insert? We first figure out what is the index in the array list where this goes, right? And that would be the size of the array list at this point. So mlist dot size. I think there is a size. I'm going to open Java's array list as well. Okay, so let's look at that quickly. Yeah, the size is the number of elements in the list. Okay, so the size is going to be our next index where we insert, right? And so what we do is we just add an entry to the map and add this element to the array list. So let's just do that. So map mlist dot add, and we just say val, right? And it will go at this index, right? Because that was the size before. Okay, and then we say m map dot, I think, put key comma value. So key is our value and value is our index in the array. And there you go. So return true, right? We successfully inserted. Okay, so I think the insert operation was reasonably straightforward. Now remove, yeah, this is going to be the trickier operation, right? But again, first we check whether it does not exist, then we return false. So map, again, when we want to check efficiently by the value, we use the map, right? So map dot contains key of val. If not, and we return false, right? Okay, now we go slowly. Let's revise here. When we removed 7, we first looked up we first looked up 7 and looked up what its index was from the map. Okay, so int val index, let's call it val index, equals mmap dot get, I think, and val, right? Very quickly, I think get is the one that gets by key. Yeah, there you go. So it gets us the value by key. Okay, so we got the val index. Now what do we do next? We have our val index from here 1. We go there and we want to kind of replace the value of this with the last value. Okay, so let's do that. Int last value equals mlist dot get and then mlist dot size minus 1, right? That's the last index. And just very quickly, I just want to make sure that there is a get like that, which can get us by index. Yeah, there you go. Okay, so we do that. Okay, this needs to be this. Okay, yeah, there is one extra bracket there. Okay, got it. So that is the last value. And what do we do in the list? Again, we put at that index, val index, we put the last value, right? So again, we put at this index number 13, right? So that is done now. And I think there is a put or set. Let's see, it is a put or set. Well, actually, it's a set. Okay, so this is not a put. Put is generally used in maps, I guess. Okay, so mlist.set at that index, the last value, and now we remove it from there and we remove it from the map. We still haven't removed it from the map. Remember that, right? So far we only done read-only operations. So we say mlist.remove and then we say mlist dot, actually we can just give, yeah, mlist dot size minus 1, right? So we remove the last element. Again, let's make sure there is a remove method which takes index, remove, no, I'm in the wrong, yeah, array list is what I want. I was in the hash map one. Yeah, remove int index, right? So remove the element. Okay, sounds good. So we removed the last one. So I think the array is now all set. We have replaced 13 here and we removed this guy. So now one can, but we haven't updated 13 to 1 there, right? So we need to do that first. So in the map, actually let's do all the read operations, or not remove, mmap dot dot put, and I think we can do last values is at val index now, right? And then we do this and then we just remove from the map. Map dot remove just last val, not last val, sorry, val. Okay, because that's what we are removing, and then we return true. Okay, so let's just go through this one more time. I know it's a bit long, but we just want to make sure. So remove, we are removing 7. We look up 7 and we found 1. So that's what we did here. We said 7 is at 1. And then we said what is the last value. We're just reading it. The last value is 13. Okay. Then we said in the list set at val index, set that to 13. So we have actually set this to 13 at this point. This is still there, but we have set this to 13. And once we set that to 13, we want to make the map also synchronous. So we said in the map, the last value's index is now val index. Okay, that's great. So that keeps the map in sync. And now we remove from both the map and the list. In the list, we remove the last value because this was already overwritten. So this is the last value. And then in map, we remove the value. Okay, there you go. I think that's good. Okay, let's get to the random. I think in random, we first generate random number between 0 and the size of the array. So I think we need this. Okay, And just very quickly, I do not remember the exact syntax, but I think it has a method to generate an integer in a range. So let's look that up very quickly. Not ints, these are all streams, so they give us a stream to generate multiple one by one. I think this one, next int and bound. Okay, and it returns as a uniformly distributed int value between 0 inclusive and the specified value exclusive. Okay, it's good. This is exclusive, right? So we can just give it the size of the array, not size of the array -1 because it's already exclusive. Okay, so we say int random index equals rnd dot next int, and we just give it the m list dot size, right? M list, correct? Yes, m list dot size, and we just read from that m list, return m list dot get random index. There you go. Okay. Oof, okay, so I think it took a little bit longer than I thought, but I think this was important to get the details right. Well, we still haven't made sure it works. So let's actually run this and make sure it works. Okay, compiler should be reasonably easy to fix. Private. Oh, yeah, it's just a transposition of 2 letters. Okay, let's see. Oh, mmap, right? I mean, I named it mmap and I probably used map in a lot of places. So let's see here. Where all mlist, mmap, this is fine. Again, here, mmap, and then mmap is good here. Mlist, mmap, mmap. Yeah, I think that doesn't use a map. Okay, hopefully. Okay, one more. Random index. Okay. Well, looks like I am not typing very well today. There you go. Okay, so it says accepted, and but there's only one test case here. Now we could add a lot of test cases ourselves, but I would instead just submit and let it run a bunch of test cases, and that will also give us the performance of our code against all other successful submissions. Okay, it beats 47.2%. Okay, I expected more, but I mean, it's supposed to implement in O of 1 time, so I suppose everybody's successful submission is O of 1 time, but it did accept it. And well, memory beats 99%. Okay, that is very interesting. Oh, you know what? I think one thing I can do, I don't know if it compromises the randomness, but I did notice that when I did this, but I could create a shared object here and just use that, right? So mRandom, and then let's just initialize that in the constructor. Don't want to make this video very long by checking whether this is actually compromises the randomness or not. If it doesn't, then we can just create a shared one, right? Okay, and then we just say mRandom. Let's see if this helps. Well, first let's run it and make sure I didn't screw up anything. Okay, so that got accepted. Not sure if that it could. I mean, it creating. Okay, so there you go. That actually improves how many we beat by or our percentile. But again, in reality, I would actually check whether it compromises the randomness and uniform distribution or not. But there you go. Hopefully that was helpful. If you're liking what I'm doing on this channel, please consider to subscribe to my channel and give a thumbs up to this video. Thank you so much. See you guys next.